Right. Hello, everyone. So let's see the last presentation that's pertaining to the beam matrix, beam stiffness matrix. We talked earlier and we had three examples on beams, how to develop the stiffness matrix for the beams, how to solve F equals K times D, and how to find the unknown displacements and how to find the reactions. Now we're going to be talking about something similar for the same exact loads that we have, same exact beams that we had. We might encounter some sort of intermediate loading. What I mean by intermediate loading, that we are going to have load that they are not at the nodes, non-nodal forces. So you have the beam, you not necessarily have force right here and there. You can have a concentrated load here at the center or distributed load throughout the beam. How can we deal with that? The procedure is that we restrain the members from all movements at both ends. And then we get the reaction produced by the non-nodal forces or the distributed forces right here, and what we call fixed end forces. We don't have to find it, it's in the back of any structure analysis book. We can find that. And then we change a sign, and these are something called the equivalent nodal force. So ultimately, the ultimate goal is that we come to this force equals K times D, but we add to it another Q equivalent for the effect of this fixed end force. It's going to be negative, and this is going to be negative, so both are positive. I'm going to explain to you that in a little bit. So, for example, if you have a beam that is subject to certain loading right here, P, you know the effect of this P right here is pushing half of it, P over 2 here, and half of it, P over 2 here. And the fixed end moments here and there is PL over 8. And the reaction is going to be opposite to this. So if these forces are pushing down in the same direction of force, the reactions are going to be opposite. And that makes sense. If I'm standing right here in the middle of the beam, the support reaction is going to be half of my load, opposite to this gravity load, and the support reaction here is going to be half of my load and opposite to the gravity downward load as well. And the moment or the couple that's produced at the fixed ends is going to be opposite to the one at the left hand side. Same exact thing happens if you have a beam that has distributed force. The effect of this distributed force at the nodes are WL over 2 pushing down here and there, and the reaction is going to be opposite. And moment, which is WL squared over 12, clockwise right here to the left node, counterclockwise to the right node, and that makes perfect sense if you have a beam that's subject to load. So the deformation happens like that, so you'll have moment right here and moment right there, and the reactions are going to be different. How do we handle them? The left part right here will be already handled by the stiffness matrix. This one right here is going to be added to the solution as we had earlier in this slide. I just want to point out that if you add those together, guess what's going to happen? You will end up with the same exact load, with the same exact beam that you're having. So let's see exactly what we're talking about. In another way, it's important that for the element, if we'd like to analyze the intermediate loading, the element should be free of loading throughout its length, right here. And this is necessary since the stiffness matrix that we're going to be developing here, it was developed for while the loading at ends only, nothing within the beam. Plus, another case while we're having the beam with the intermediate force and the reaction. So if we add those together, what you're going to end up having is a beam that has load right there. I just want to point out something here in the previous slide. Please forgive me, just remove the loads here and there from this so that when you add them up, it will give you the actual scenario. Like this case, for instance, you have the beam that's free of any load and then the reaction at the very end. So let's see. Member forces, we are going to get the shear and moment at ends of the beam using Q, or the force equals K times D, as we've done earlier. Then add to it another vector, which is for the fixed end reactions, Q naught. And that will be this equation right here, which is Q equals KD plus Q naught. Once you get the resultant, if it is negative, that means that the loading or the force is acting opposite to the direction that is shown right here. So these are the positive direction going up, and these are counterclockwise is positive direction for the rotation and the force. So let's have an example. If you have that beam, which is two pieces with three supports, the first panel span has 50 kilo pounds at the center, and the second one has distributed force of 3.6 kips. We are going to identify the nodes, which is 1, 2, and 3. Identify the members 1 and 2. We're going to identify the degrees of freedom. So I'm going to start knowing that no translation or displacement at this end, 4 and 5 and 6. So let's keep them to the end. Start with 1, 2, and 3 for the degrees of freedom, since these are unknown deformation, unknown rotation, theta. So 1, 2, and 3. However, the displacements here is 4, 0, 5 is 0, 6 is 0. And let's do the nodal. Remember when we talked here, we said that we'd like to get the fixed end reactions and all this stuff. Let's look at that closely and see. If I have 50 kips applied here at the center, it has an effect of half of it, 25 and 25. In the second span, 3.6 kips foot times 12, divide by 2, that will give you 21.6 here, 21.6 right there. So basically, the forces that you're having at this end, you have 25 kips. At the intermediate support, you have 25 plus 21.6, that will give you 46.6. At this end right here, which is at degree of freedom 6, you have 21.6. All right, let me repeat that one more time. You have a concentrated load that will be divided into 25 and 25 with negative sign. A distributed load that will have WL over 2 here and there. Then at degree of freedom 4, I have 25 kips. Here we go, negative 25 kips. At degree of freedom 5, what do I have? These two loads. So I have negative 64.6. How about degree of freedom 6, which is the vertical one right here? How much load we have? 21.6, and that is negative. Let's go to the theta and the moment. The application of the load here will have a moment which is PL over 8. So the PL over 8 will give you 62.5 kips foot, which is the same as 750 kips inches. And that is clockwise, but we assume that the counterclockwise is positive, so it will be negative 750. Here you will have PL over 8, which is another 750 positive, but we have an effect of the distributed load. What is that again? If I go back a couple of slides and see, if I have a distributed load right here, I will have WL squared over 12 and WL squared over 12. So when you apply that in this example, you get 43.2 right here and another 43.2 right there. But pay attention that this node is subject to moment coming from the concentrated load, another moment that's coming from the distributed load. So what do we have at degree of freedom 1? Only the 62.5 kips foot, which is 750. What do we have at the very end right there? 43.2 kips foot, which translates to this 518.4. How about here at the intermediate one? We have the difference of these two, whether they are added together or subtracted from each other. In that case, they are opposite to each other. And this is 62.5, this is 43.2. You add them up, and that will give you 231 kips inches. Fantastic. These are the forces. And then the displacement that we're having, D1, which is rotation, 3 thetas, 1 at 1, 2, and 3 degrees of freedom, unknown. However, the displacement 4 and 5 and 6 are zeros. Fair enough. And the forces that we're having, the unknown forces are F4, F5, F6, which is the reaction here, here, and here. How about F1, F2, F3? Do we have any applied moment? No. So this will be 0. When we apply that, we have to find the stiffness matrix for the first element, stiffness matrix for the second element, and the label of the degrees of freedom 4152 for element 1. Let's see if that's correct. 4152. What do you think the second one will have? 5, 2, 6, 3. Let's see if we have that. Yes, 5, 2, 6, and 3. Add them up, come up with this big matrix and the partition after 3 elements, and this is force equals K times delta. From that, you solve as we did earlier for delta 1, delta 2, delta 3, which are the 3 rotations, and then you come up with the force matrix that we're having, and that force matrix is F equals K times delta, which is this force equals K times delta, but you add to it another matrix, and pay attention. The negative 25, negative 46, and negative 21, and another negative right there, they will be added together to come up with 17.2, 60.89, 15.1, and these are going to be the forces that they are developed at the 3 ends. And then if you would like to get the member forces, all you need to do is find out where is that member. This is the first member, which has 50 kips at the center. Let's look at it together. Force equals K times delta. Where do we get that? Let's go back a couple of slides. Go to this stiffness matrix of the member 4152 and bring it here. Here we go. You have this stiffness matrix times delta. Which deltas we're talking about? This member has 4 and 1 and 5 and 2. So we have 4 is 0, 1 is negative 0.5 something, here we go. 5 is 0, here we go. And 2 is from the solution that we have is 1.68, 10 to the negative 4. You plug it right here. So K and delta, but don't forget to add to it the applied force that we talked about. What applied force? What is this 25 and 750? Let's go back. The 25 is right here, and this is the 25 and the 21.6, as you can see right there, and the moment. So here we go. You put the matrix for Q naught, you add them up, you came up with this member forces. 17.2 rotation, vertical displacement, vertical reaction right here as far as shear, and moment is 0, and that makes sense. At this end, I have a reaction of 17.2, and that will be the shear thing, and I have 0 moment right there. How about at this end? What do I have? We do have 32.8, here we go, and that is the reaction, and negative 935 kips foot, or rather, I'm sorry, kips inch, and that is basically the moment right there. So I can plot the bending moment diagram for this member, knowing 0 moment right here and maximum moment right there, and you have this kind of PL over 4 that you can construct the bending moment. So can I repeat that for another member? Absolutely. For this member right there, you can have Q equals K times delta, and then you add this load or Q naught, the forces, to come up with the final vector for the reaction, moment, reaction, moment. So we have 28.1 as far as the force at this end, and the moment is 935 kips inches. You convert it to kips foot, and then reaction of 15, and the moment is 0. You come up with that shape, and that is second degree parabola because you have distributed load right here. Can I add these two members together, assemble them? Here we go. We assemble those. You have the first bending moment as you had it from this figure, and then the second one right here, it will be added right there, and you are done with this example. My homework for you is this one right here. You have a beam that has 24 feet subject to 2 kips foot, and then you have another beam which is 8 foot. At the center, you have 12.